Today we're going to talk about self-supervised learning. This is a lecture that that doesn't have a lot of math, but it's going to be all about very recent works, probably in the last 3 or 4 years at the most. So, and these are kind of a pretty interesting, kind of intriguing kind of concepts, but nothing very complicated. Everything is kind of simple. So basically, I think about probably 2013, 2014, I think deep learning, neural networks, these kind of ideas start to take off, and we have this kind of like a revolution of AI in some sense. We have a lot of amazing results in the last about 10 years, right after deep learning took off. But in the last 2 or 3 years, I think we see kind of like an emergent new paradigm of AI, which is still based on deep learning neural networks, but I think kind of in some sense the paradigm shift a little bit towards this kind of large-scale unsupervised learning or self-supervised learning. So that's kind of what we're going to talk about today. So I guess last few lectures, I think Chris talked about unsupervised learning. So those are mostly ideas, more classical ideas that was developed before deep learning took off. And today, I think we're going to talk about the kind of new type of unsupervised learning, which is not that different from the old ones, but with neural networks and with some more some kind of technical differences and also some differences in the conceptual way. So I think in some sense this is called actually we also read a white paper about this a bunch of Stanford people, actually there are 100 people, more than 100 people on the paper, so mostly Stanford researchers, Stanford faculty and students. So we wrote a white paper on this. We call it foundation model. So in some sense it's just a name. So it's a name for kind of this large set of ideas that involves kind of pre-training on unsupervised data and then kind of use it for a bunch of downstream tasks. I'm not sure whether you know any of these buzzwords, but that's what I'm here for. So I'm going to define some of these words and tell you what's kind of the pipeline and the paradigm is. So basically, kind of the main thing for deep learning is that we use neural networks to fit larger data than we used to do before, 10 years. 15 years ago, and typically at the beginning when you use deep learning, you use it for supervised learning, right? You have a lot of data, maybe 1 million data in ImageNet, and you have labels for them, and then you fit a big neural network to predict the label. And it turns out that even your neural network is pretty big, as long as your data is also somewhat big, you can see good results. And sometimes you can even make it work on small data. So, but all of this requires some amount of label data. Right, so and then recently people figure out maybe we should use unlabeled data as well, right? So when you use unlabeled data, then you have much more. For example, for text data, I think there's this data set which has 40 trillion words in it. But if you have labeled data sets, then you probably have 1 million labeled documents, and also a label has specific meanings, maybe you need multiple labels for a document, right, in many cases. So if you say I can train with unlabeled data, then you suddenly have availability of a lot more data. So I think that's kind of the main kind of the driving force. So now we are training on unsupervised, on unlabeled data. So and this kind of and how do you train with unsupervised, unlabeled data? I think often people have different words for the same kind of concept. I think one of the way to call it is called self-supervised learning. So you supervise, as you will see, you're going to supervise your model with yourself, the input itself. So you don't have to use any label. And sometimes, as I said, in a white paper, we call this family of models called foundation model. Foundation. It's kind of I will explain this word a little bit more. And some other buzzwords include pre-training. I'll explain them as well, and adaptation. So I guess I will just start by explaining pre-training. So in some sense, the way that people do this right now is the following. So you have this so-called pre-training stage where you pre-train. So large scale, and here large scale really means very, very large scale, unlabeled data set. It's not always the case that you have to use an unlabeled data set. We'll see actually in some cases you can use a labeled data set for pre-training, but you really have to make it large scale. And an unlabeled data set is kind of more common than labeled data set. And also you pre-train a large model, a very large model. And then the second step is that you somehow adapt this. So adapt this pre-trained model to some downstream tasks. Actually, often you can adapt to many downstream tasks, not only one. But adaptation to many tasks is the same as adapting to one. You just do it one by one. So you adapt to some downstream tasks. And these downstream tasks are often labeled data sets. So, and for downstream tasks, you have different settings. I will describe, in more detail. But generally, you have, a few examples, in a downstream task. For example, one example could be that, you pre-train on unlabeled text, right? That you can download from internet, right? So you could have like a trillion words, like documents, like a lot of documents with a trillion words downloaded from internet, and you pre-train your model on this unlabeled data set. How do you pre-train? I'm going to tell you. And then after you get this model is pre-trained, with no labels. So it doesn't really solve any particular task. And then you say, I'm going to have a downstream task about text. Maybe I care about sentiment analysis, meaning you care about whether a document or a sentence is positive or not, right? Maybe for Amazon review, right, you care about whether the review is positive or not. And then you say, I'm going to have a small number of examples for sentiment analysis. I have a small number of examples with documents and label the positive or negative label pair, right? So maybe like 100 or 1,000 kind of like pairs of documents and label. And then that's called downstream task. And then you want to adapt your pre-trained model, which is very generic, to the specific task using some additional kind of like tuning. So that's the general idea. And sometimes, of course, kind of the distinction between these two steps is that this step, you may still involve some training, some kind of training in this adaptation step, because you're going to see the new examples on a downstream task, the sentiment analysis tasks, right? And then you have to kind of do something, with those examples. So there's possibly a training or optimization step in the adaptation step as well. But the difference here is that this step often involves very large-scale data and is kind of generic. It's not like about task-specific learning. So here it's really about the task itself. And also oftentimes you have much fewer data points than the pre-training step. Sometimes you have 1,000, sometimes you have 10,000, but generally not a lot. Sometimes you can even work with even 0 examples in adaptation step. You can sometimes still adapt to the task. So kind of the intuition is that the pre-training step is about learning the generic structure or the kind of like the intrinsic structure of, for example, texts, right? For example, if you do it for image, you are learning the intrinsic kind of like structure of the images, maybe the kind of the intrinsic features about images. And then the adaptation step is more about the task itself, right? So for images, you can care about the many different tasks. Maybe you care about recognition, maybe you care about classification, or maybe you care about different kind of like labels, right? So you can have labels of different granularities, a bunch of different tasks, right? So this step is more about tasks. So that's the kind of like the general kind of like intuition, right? You pre-train on a lot of data, so that give you the intrinsic structure or the intrinsic representations for this kind of data, and that representations are useful for downstream tasks, so that you don't have to use like a lot of examples in downstream task, right? Because you already learned some intrinsic representations that helps you for the downstream task. Right. So basically, the kind of the one implication here is that you expect that this pipeline is going to do better than just training your model only on the downstream data set. So that's the basic goal, right? You have the baseline is that the trivial baseline is that you just directly train your model on the task, downstream task. But generally, you don't have enough data for that. But if you do this kind of like transferring from the unlabeled data set to this one, then you may do better. And we call this kind of like pre-trained model also foundation model. So here I call it pre-trained model, right? So you can also call it foundation model. And the reason for the word foundation, I think the kind of like the implication is that this pre-trained model is kind of like a general model that, general purpose model that can do a lot of different things. And that's kind of the foundation. And this is the adaptation. Yeah, I haven't talked about weights yet, right? Yes, but that's a good question, but I'll talk about those. Yeah. Okay, any questions so far? So I'm going to tell you, okay, so this is the general idea. I'm going to tell you some kind of like, I'm going to start with some simple notations and tell you how do people generally do this in a more kind of mathematical way. Okay, so pre-training. So I guess, so let's say you have some data, something like x1 up to xn. So you have n data points, and n could be very big. And there is no label here, so this is unsupervised, pre-training. Of course, sometimes you can still have labels in it, but let's say we focus on the case where you have no labels. And you have a model. So let's specify the input and the output of the model. So typically you can think of this as, the model, let's say, is called phi of theta. In some sense, you view this as a feature extractor, a feature map. But it's a learned feature map. So this is something that maps x to phi of theta. Phi theta of x. And let's say phi theta of x is some vector. So, and I guess you can, as we have kind of seen, this kind of like when we have this kind of feature map, often you call this representation, features, there are many names for it. Representation / features / sometimes people also call it embeddings, especially if you talk to more mathematical people, because in math this word embedding is used in a similar context. So this is a representation of the raw data you have, right? So the raw data could be text, could be image, and this is a vector. So this is something we are familiar with, right? So in both neural networks we have viewed the last but one layer as the representation. In the feature lecture, this is the feature map. Although like in the kernel lecture, this is the feature map, but in the kernel lecture, this feature map is given and designed. But later, when we do the neural networks, this is the learned feature map. And here we are still learning a feature map. Or we are still learning a feature map, feature extractor, whatever you call this. So, and then, but here you learn this, without labels. So you say you have some pre-training loss, maybe some pre-training loss. There are many forms of pre-training loss as well. Here I'm just only giving one form, something like probably nothing, maybe some loss on like a sum of loss on single example, right? So I'm going to define the loss for different cases. Sometimes this loss can also depend on multiple examples. Sometimes it can depend on labels, but something like this. You have a pre-training loss. Okay, and then what you do is you just optimize this loss. This L pre theta, and let's say obtain some theta hat. So and I'm going to call this my pre-trained model. Or maybe we can call it foundation model or something like that. Okay, so nothing fancy so far yet. I haven't told you what the pre-training loss is. There are many different ways of doing pre-training. I'm going to tell you a few ways. But so far, it's just you have define some loss function, but the loss only depends on the unlabeled data, and then you minimize the loss and you get some model. Okay, so, and then I'm going to do the adaptation step, which I'm going to be a little bit more concrete because it's a little bit easier. So in the adaptation step, let's first clarify what kind of data you have, right? Before talking about how do you do it. So what data do you have? So you can, often it's a labeled data set. It's a labeled prediction task, the downstream tasks. Even though I think, if you look at enough papers, there are many other papers talking about different type of tasks. But here, let's say we have some labeled, some prediction task, and we have some labeled data set. So let's say we have a few examples, let's call it X task 1, Y task 1, so on and so forth. X task NT, Y task NT. And this is the number of, downstream examples, which is, presumably much smaller than, like I'm going to use NT as the number of downstream task examples. So, and this one, this is supposed to be much smaller than the number of unlabeled examples in the pre-training step. So, and there are actually a few different settings, So one setting is that when NT is 0, so this is called zero-shot learning. So when NT is 0, it just means you don't have anything. You don't have the data set. So it's called zero-shot learning. We'll see how do you do it. Sometimes you can still do zero. Like you can still do the task without even knowing anything about the task. And when NT is relatively small, I think this is called few shot. And what do I mean by small? I think in the literature, maybe 5 is typically considered as small, 5, 10, 20, but maybe not more than 50. If you have more than 50 examples, I think, of course, there's nobody really defined what exactly it means, but I think if it's more than 50 examples per class in the downstream task, I don't think you would call it few shots. So mostly like 10. So, but of course, there are cases where you can have more examples. Maybe like, I think I've seen cases where you have like 10,000 examples, or maybe even 100,000 in some extreme cases. So, but the N there typically could be like a billion or even a trillion sometimes, 100 billion. So, okay. So so this is the setup. I'm giving this information, and then how do I do it? So on a high level, the first thing I'm going to do is I'm going to first define how do I adapt, right? So I'm giving this model theta hat. So what's the model to predict a label? I need to have a model that predicts a label. So here the theta hat predicts a feature vector, but not a label. So the first thing is that I'm going to typically I'm going to have some kind of like maybe let me introduce one way to do this. So which is called linear probe. Often people also call it linear hat. Like something like this. So the kind of like the idea is, you probably should be familiar with this. It's just like you take this feature, phi theta hat x, and then you apply a linear classifier on top of it. You say, I'm going to take an inner product of this feature with some linear classifier w. And w transpose x is my prediction model for the downstream task. Let's say suppose you have a regression model, then you just want this to be some real number. And if you have classification, then this is supposed to predict the probability of the label, of one of the label. So it's just almost the same as what we do in networks, right? You just you have some feature and you apply some linear hat on this feature. So and then so if we'll do linear probe, what we'll do is that this is we have defined a prediction model. And then you can define you can say, how do I learn this W? Right? So here, note that theta hat here is fixed. So I'm only learning W when I'm doing a linear probe. So how do you learn W? You just say, I'm going to just tune W with some loss function, with some loss function on the downstream examples. So basically, I just do something like maybe 1 over nt and minimize over W, and I have a loss function, which is the sum over the loss on downstream tasks, assuming you have downstream tasks, right? Or assuming you have downstream examples. If you don't have downstream examples, this doesn't apply anymore. I'll tell you how do we do it when you don't have downstream examples. But suppose you have downstream examples, then you just minimize the loss, something like the loss, let's call it L task, and this loss function is something that compares the label and your prediction of your model. The prediction of your model is something like this. Right. This task, for example, could be just L2 loss, mean square loss. This loss could be just the mean square loss, or could be some kind of cross entropy loss, or some other loss that you care about. And so when you do so-called linear probe, it means that you only optimize W. So you are only optimizing W, which is a vector of dimension m, right? So m is W is in Rm. So you are just optimizing this m-dimensional vector to make your model fit to the downstream task. And this is the so-called adaptation step. Basically, the W is the thing that you want to use to adapt your model to the new task. Any questions?
Where do the labels into downstream tasks from doing manually label?
So where the label come from? You assume you have a label data set. Somebody gave you, right? So you collect the data set as the same as what we did before. But the difference is that you may not have to collect as many as before. If you just tune on this data set just from scratch, then you may need more than what you do here. Okay.
About terminology. So when pre-training, does it has the same meaning as transfer learning?
So I think I guess maybe the question is what transfer learning come into play here. So I think you can in some sense call this also transfer learning. So transfer learning used to be the transfer learning word occurs like this term was used way before people have done any of the pre-training. So now I think the transfer learning probably people studied in early 2000 already, even maybe before that. So at that time, transfer learning means what? It means that if I use pre-training language, it means that you pre-train with a label data set, and then you do some adaptation. So basically, transfer learning means this in the new language. So but now these days when we pre-train on unlabeled data set. And another thing is that it used to be the case that when transferring the first data set you train on is classification task, which is kind of similar to the final task you care about. So but here in some sense the reason why people introduce new terms for this is that when you pre-train, this task could be nothing like the downstream tasks. I haven't told you what exactly the task is, but at least you can imagine there's not a lot of similarity because here you don't even have labels. Right? It has to be something different. Yeah, but I think you can still say this is transfer learning. It's not like there's no precise boundary between this. Okay, so let me introduce another way to do adaptation. So another very common way to do adaptation is that it's so-called fine-tuning. And it's also pretty easy to understand. So basically your model is the same. But your prediction is some W transpose phi theta of x. So here I write theta but not theta hat to indicate that I'm allowed to change this theta. So here, theta doesn't have to be exactly the pre-trained model anymore. It could be something that you can change. So then what you do is you say, I'm going to optimize both W and theta on the downstream tasks. But if I just say this, then this just sounds like the standard supervised learning, right? There's nothing different from supervised learning. You are just training some neural network, right? W transpose phi of theta x on the downstream task. The difference from that is that you optimize, but you also initialize with initialization that theta is initialized to be theta hat. Recall that theta hat is the pre-trained model. So basically, you just train as if you are doing supervised learning, but theta is initialized to be theta hat. And W, there's nothing you can do with it, right? Because you didn't know W before. So W is something new. So you just initialize W to be random. So that's so-called fine-tuning. And you can optimize the same laws or whatever laws you care about. That's our question. Theta is the parameter for this function phi. Phi is a function parametrized by theta. So that's what?
Like similar to how we use feature change the parameter into the feature space.
No, I think I just mean that this is just phi is just is a name. Is just is a you can call it a f sub theta. This is or h sub theta. It's just a name for this model that is parameterized by theta. So think of phi theta is the neural network with parameter theta. I just need a notation to indicate this function, right? I cannot just write theta. Theta and phi theta, they correspond to the same thing, but mathematically I have to write phi sub theta of something to indicate that I'm applying this model on x. Dimension of theta I haven't specified. It could be anything. So I can give a name for it. Let's say dimension is p, but it's not. I didn't use it explicitly yet. But dimension of theta, it could be big. Any other questions?
Yeah, it was just relating to the loss function for the pre-training data. Having trouble understanding clustering and the.
Right. So I haven't told you yet at all. So just because there are so many different variants, I have to somehow do it in a top-down fashion. So here for the downstream task, I can do it just because these two things are very you can use this for almost every situation. But when you talk about pre-training, I have to talk about what you do in computer vision, what you do in language. At least there are some differences depending on the domain. Of course, there are also kind of recent works that try to unify all of this, but at least I have to somewhat talk about the domains. And that's what I'm going to talk about next. Yeah. Okay, cool. I guess maybe I'll just do that. So how do we pre-train, right? So I'm going to pre-train a representation. How do we do that? So let's first talk about the vision settings. So or more kind of like the classification, like the standard kind of classification settings. So let's just for simplicity, just think of like a vision. So suppose you have some kind of like images, right? So there are two types of pre-training. So one type is called supervised pre-training. You may wonder, why, like I already emphasized so much that the pre-training should be mostly on unlabeled data, but actually for vision, because you have a lot of labeled data, all right, the ImageNet is a pretty big data set, so you can actually do supervised pre-training as well. And this is just exactly what we have seen before. So you can just, what you do is you just learn a neural network. Let's call this neural network, maybe let's call it U transpose phi of x on labeled data set, say ImageNet. So And here the notation is that this is the last layer of the neural network. Right, the last layer was linear, right? Recall, right? So, and phi theta of x is all the other layers, right? It's basically the last but one layer activation. Right. So phi theta of x just denote what you do in the first r-1 layers, and then u transpose means the last layer of the network. And so theta, of course, so basically if you have a neural network like I don't know whether this, I think we discussed this, in one of the lectures. So in deep learning, right? So you have a neural network, you have a lot of connections, and eventually output some y. And you view all of this as your phi of theta. And you view this as the so-called u. And sometimes people call this linear hat, right? So you just do this, this is just exactly as what we do in the neural network lecture. And then you just discard, u. And just take the phi theta of x, right? The learned as the pre-trained model. So you think of this as the feature, and this is you think of this as a kind of a universal feature in some sense. And the head is special to the tasks you use, right? To the label data set you use, right? Maybe you use ImageNet. The head has 1,000, like classes. That's something special. But the features is something kind of more universal. You just take the features and discard the head. And then once you have a new task, maybe not ImageNet, maybe some other classification task. Maybe let's say now you have a new task which is medical imaging, right? Like you are detecting from a scan image whether some person has, let's say, cancer, right? So then you just take this part, this phi theta, and then you apply a new head, right? I'm using W as the new head, right? You apply a new head, and then you fine-tune all just a linear probe on your downstream task, right? So you remove this head and apply something else, and then you do some training on a downstream task. So that's the supervised pre-training.
You gave, if you're like the medical images are like a different size than like the ones that it was pre-trained on, what kind of like stuff do we need to do to make it work?
Yeah, I think typically if the size are different, you just have to upsize. I'm assuming maybe medical images has lower resolution. You just have to do some kind of upsampling of the sorry, what's the right word for it? Like you just make the size bigger. I think you can pack either you can pack some zeros outside, or you can just maybe replicate the pixels somewhere. There's nothing fancy.
Also, you mentioned earlier that like if the task isn't similar, it might not work as well. So like, is that a concern here?
So here at least methodologically, you don't have to concern much because of that, because your, let's say, the pre-trained images, they have the ImageNet classes. They are all like sometimes animals, all kind of like common objects, right? But anyway, you discard the head. You remove the head, and then you add a new head. Maybe now your new task just have two labels, right? Cancer or not, right? And you just apply to that. So in terms of the method, at least you can apply it when the task labels are different. But whether it will work, sometimes depends on how different your new task is from the old task. So typically, if you use ImageNet pre-training, you always learn something reasonable about the features. You wouldn't be terrible. But if your task, for example, your downstream task is really not even common images, nothing like that's just some kind of like a random images, then probably it wouldn't help that much. Okay, so here there's nothing really that's fancy, and people kind of like did this anyways, like in the beginning of the deep learning era. And there are some other kind of like, and the second one I'm going to talk about is the so-called contrastive learning, which is now unlabeled, like an unsupervised learning algorithm for pre-training, or people call it self-supervised learning. So contrastive learning. So now I don't have any labels. I just have an unlabeled data set. I need to define a loss function on unlabeled data set. So how do I do that? So I need to first introduce a notion called data augmentation. So a data augmentation is something that, as the name suggests, you are augmenting one example into a artificial example that still makes some sense. So, and typically for images, what you do is you just say, I have an original image. And then you augment by doing some kind of like so-called you can do a few things, maybe random crop. So you crop a patch of the image as a new image, or you can apply a random crop plus a flip. You can flip the image, just with a mirror flip, and or you can do some color transformation. Color transformation means that maybe you make the image darker, brighter, or sometimes you can just even do weird, more weird kind of like color transformation. You change all the brown color to the white color, like you can do some kind of like changing of the color scheme. And there are many others, some of them are more advanced, and sometimes you can even learn the transformation. But these are kind of the common ones. So basically, given an image, you can do these random operations, kind of like you can choose to flip or not. That's a random decision. You can choose to crop which part of the image. Like you can do some kind of like random color transformation. So you have some randomness here. And then given an image X, basically you can generate a random augmentation that's called X hat. And if you do this again, you can generate another one, which I'm going to call X tilde. And if you do it more and more times, you can generate even more of these augmentations. So these augmentations was used in supervised learning actually as well. We didn't discuss them just because they are low-level details. For supervised learning, what you actually do is that you can give an image and the label. You can generate the augmentation, and then just assume the augmentation is your new image. So you just replace the old image by the augmentation. And every time you do this, with a new augmentation, like every time you see this image, you replace the image by a new augmentation and train with that augmented images. And that seems to improve the, in some sense, you make the data set bigger in some sense, because these are, every time you augment, right, you're going to get a different image in some sense. Even though they are somewhat similar, but still you make the effective size of the data set a little bit bigger. So that's why people use it in supervised learning. But now I'm going to use it in unsupervised learning. Actually, now people call it self-supervised learning. So I'm going to use this to create some kind of supervision or kind of create some kind of unsupervised loss. What you do is you say, I'm going to call this X hat. First of all, I'm going to define some notation. This is called a positive pair. So positive pairs are augmentations of the same image. So one, you can imagine, one property of the positive pair is that these two augmented images, are probably should be somewhat similar semantically. Even though they may not have the same color scheme, they may not have exactly the same orientation right? So they are still somewhat similar semantically, right? So what you do is you say you are gonna try to make, so you're going to design a loss function such that, one, you want to make phi of theta of x hat and phi of theta x tilde close. So basically you say, I have two augmentations. One is x hat, the other is x tilde. You want these two augmentations to have similar representations in the Euclidean space. So that's one goal of the loss. I'm going to tell you exactly what the loss looks like, but this is one goal of the loss. But if you just have this goal, you can see that this loss function is a little bit kind of questionable in some sense, because maybe you should just map every image to the same point. Then everything has exactly the same representation. Then you satisfy this goal. Right? So it's ideal that you should have something to counterbalance to avoid you to just collapse everything into one thing. So how do you counterbalance? The way you counterbalance is that you just to say you want random images to have different representations. So let's erase something here. Which one I should erase here probably. So basically, to counterbalance this, the second goal is that you want, suppose you say, I'm going to have some two random example. Let's say you have maybe X and Z, so maybe a cat and dog, right? And then you augment X into X hat as the same way here. And then you augment Z to Z hat. So because X and Z, are two different images, maybe one is cat and the other is dog, so their augmentations probably looks very different as well. And the augmentations are semantically very different. So then your second goal is to make phi theta x hat and phi theta z hat, the augmentations of two different examples are far away. So this is to counterbalance, to avoid you to collect everything to the same point. And actually there's a name for this pair. This x hat z hat is often called either a random pair or negative pair. So at the very beginning, I think people you call it negative pair, which is not exactly right in the sense that X and Z are just random choice of two images. There's no guarantee that they don't have exactly the same, they don't have the same class or same kind of like meaning, right? There is some small chance that both X and Z are both from the same class, right? Even if you have like 1,000 classes, there's still a little bit chance that X and Z are from the same class. But in most of the cases, X and Z are from different classes, and they are semantically different. So random pair might be a little bit more accurate, but negative pair is what people call it at the beginning. And I think now people just use this interchangeably. So basically you want random pairs to have different representations, and you want positive pairs to have similar representations. So this is the design principle. How do you do this exactly? So there are multiple papers. There are kind of like at least 4 or 5 papers that use this kind of like a principle. And sometimes actually, some papers actually does even drop the number 2. You just use 1 and somehow still sometimes it works. Just because there's some other kind of like counterbalance in the system that can kind of achieve 2 without explicitly encouraging it. But let's not talk about those. Let's talk about one case where the simplest case, we have both 1 and 2 explicitly encoded in a loss function, which is called sim-clear. And this is, I think, basically the first paper that makes this kind of idea work. So how do you exactly encode these two kind of principle? So in sim-clear, what people do is the following. So what you do is you say you first take a batch of example, a random batch of example, like in SGD. Let's call this example x1 up to xb. So you have b example, and then you first do some augmentations. So you augment to x hat 1 up to x hat b and x tilde 1 up to x tilde b. As you can see, these two are the augmentations of the first example. These two are the augmentations of the second example. And these two are the augmentations of the bth example. And then here is the loss function. So let me write down the loss function and then I can explain. So the intuition is that you want to design a loss function that basically maybe let's see. So I don't have a different color today. So because these two are augmentations of the same example, you want them to have similar representations, right? and maybe the same thing happens for these two, right? So any pairs, you should have similar representations. But if you look at this one and this one, suppose you pick something like this, then you want them to have different representations. And what you do is that you make the loss function is equal to this. This is a little bit complicated at the first sight, but it's actually not that hard. So I guess here the indices is the most important thing. So this is I, this is I, this is I, this is I. And here this is J. Sorry, my handwriting is a little bit unclear. So, okay, so maybe the first thing to realize is the following. So maybe let's focus on this term. Maybe let's call this term A and this term B. Realize that this is also A, right? So just the same term. So this is really something like a minus log A over A plus B. Something like this, abstractly speaking. So, and if you do some simple math, you'll see that this one is decreasing in A and increasing in B. This is relatively easy. I guess you can either take a derivative or just at least the increasing in B is pretty easy because this function is decreasing in B and log is a monotone function and you have a minus in front. And for A is the reverse direction. So that means that if you minimize this log function, you are trying to encourage the term A to be smaller because it's decreasing in A, right? So you want the term A bigger because the loss function is decreasing A. The bigger the A is, the smaller the loss function is. So you want this A term, which is this inner product between. Actually, A term is exponential of the inner product, but so you want this A, which is equals to exponential phi theta x hat I transpose phi theta x tilde I to be big. You want this to be big. Right? You want this to be big. That means that you want this representation of the x hat I and the representation of the x tilde I to be as close to each other as possible. You want their inner product to be big, right? That fulfills our first goal, right? We want the representation of two examples, the augmentation of the representation of the augmentation of the same example to be as close as possible. That's the kind of the first goal. And then you want this B term to be small, right? Because the function is increasing in B and you are minimizing the function, right? The bigger the function B is, the smaller, the function is increasing in B, right? And you want the function to be small, so you want the B to be also small. Right? The smaller the B is, the smaller the function is. Right? If you want B to be small, and what are the terms in B? Basically, you have this kind of term. Right, this is the terms in B, where you have I and J here. right? So basically, you want to say that for different, when it's the augmentation, this is augmentation of the ith example, this is augmentation of the jth example. So their augmentations should have, should be small. So their inner product should be small. So that means that the representations should be far away from each other. Any questions?
Does this term also have exponential?
Exponential is an increasing function, right? If you want the exponential of something to be small, then it means you want the argument of the exponential to be also small. The first one is I and the second is J. So J only shows up once. All the others are I. So there are other interpretations of this loss function. I'm not sure whether they are easier to understand or be harder to understand than this. One interpretation of this loss function is that you can view this as a multi-class classification kind of like question. So you are trying to distinguish. So basically, in some sense, you can suppose you do a little bit of math. You can see that this is kind of the same laws as the following hypothetical question. So the question is that given this data set, I want to say, given, for example, x hat I, the first augmentation of the ith example, I want to distinguish which one is the positive pair and which one is negative pair. So basically, let's say, suppose you are, this is another interpretation, which I personally think is harder to understand. But let me just anyway say it. So suppose you have some example x hat I, and you have the corresponding x tilde I. So you can kind of view this as you want to, given this x hat I, you want to test which one of these B examples are the most correlated with I, in some sense. And you want the x hat I, this one, to stand out in some sense, compared to the other correlation. You want the correlation between these two to be dominating all the others, so that you can kind of say this one is my buddy in some sense. It's the other example in the pair. Yeah. So. But anyway, the exact form of the loss function is not that important, right? So there are actually other ways to implement this. It's not like it's really necessary to have to use this loss function. The principle is probably more important than the loss function. Right. So cool. So I guess just to summarize, this is a loss function that only depends on x, right? So you didn't use anything about label. So it's unsupervised or self-supervised loss function. So it's self-supervised because self-supervised just means you don't use any supervision except some part of yourself. Okay, any other questions?
Will phi in this case be like a classification, like classify which image it is?
No. Phi is still the same phi. The phi is just the feature. The feature, the representations, the function that computes the representation is the feature extractor or the something like that. Does that make sense? So phi is phi of say the output of vector. That's why I have the transpose. Okay, so the next thing I'm going to talk about is how do you do pre-training when you have language. And there, I'm going to tell you one method, which is also like a self-supervised or unsupervised pre-training, but the method is a little bit different. So, okay, so.
Just in CCR, so after training this model, we basically discard the very last layer and use all the remaining networks to perform like all the possible like image classification?
No, there's no last layer anymore here, right? Like this field of theta is a neural network, right? Like this field of theta is kind of like some neural network start from X, a lot of neurons, we draw a lot of neural edges, something like this, right? And eventually output some embeddings. This is field of theta, and that's it. That's your representation. So you don't have to discard last layer, but you have to add the last layer when you do the classification task. Does that make sense? This drawing is a little bit too rushed. But anyway. Okay, cool. So, large language models. So the first thing I need to address is that how do I encode the data, right? So I have some text, right? They are discrete words. I need to first turn them into numerical numbers. I guess, if you remember, I think a few weeks back, right? So we talked about this event model, right? This model that you encode the data by this very simple binary vector, right? Every document is encoded as a 0-1 vector of some size. So those are very simple. So today we're going to do the more realistic one. So you just but the encoding becomes easier actually, just because what you do is you just directly encode each vector, each word as just the discrete token. So okay, let me just say this. So I'm saying that this is a way to encode, but the encoding is kind of like to some extent much conceptually much simpler. So basically, the first thing is that let's define what is an example when you have like a language. So typically, I think for me the best way to think about the example in language is that you think of it as a document or something like that. A sequence of words. Because you cannot view every word as an example, then you lose the examples are supposed to be somewhat kind of like independent with each other, right? So if you view each word as an example, that's too small of a granularity. So you view each document as an example. So that's kind of the mental picture I think of. So you have a sequence of words, maybe x1 up to xt, and this is one example. In reality, what people do is that people don't really kind of like just literally look at which the documents, because what you are given is that you are given, for example, all the Wikipedia text on Wikipedia, and this is a gigantic file which is really just a sequence of words, and everything is concatenated together. And then what people do is that you just truncate, you just take a consecutive kind of sequence of like words as one example. Maybe you take something like maybe 500 words, consecutive 500 words, or maybe 1,000 words as one example. But in any case, I think if you don't care about the details, implementation details, it's just fine to think of each example as a kind of a document. An important thing is that it's a sequence of words. And there's another small detail in the implementation. So when you really do this, sometimes you don't really operate on a granularity of words, right? For example, one possible choice is you can operate on a granularity of characters, right? You view each character as one xi. People don't really do that. What people do is that people are operating on the level called tokens, and each token, typically these days in the best model, each token is kind of like a word, but sometimes smaller than a word. So basically, you can think of like most of the common tokens, most of the common words are a single token. Like the top, I think last time I checked this, it's kind of like the first like 20K frequent words are all just a single token by themselves. But sometimes you have longer words that just never show up very often, and then you break them in some way into two tokens, right? So a very, very long word might be 2 tokens. This is just another small detail, just in case you are implementing anything like this. But for conceptually, you just think of each word as a single xi here, and you have a sequence of words, t words here. That's one example. So, and then what you do is that you say, and let's say suppose you have a vocabulary, so each word is in some like set 1 to v. So you have like v possible words, and each example is a sequence of words. And when you say language model, basically people always refers to a probabilistic model probabilistic for P of the joint probability. In some sense, this is kind of like the same kind of like modeling methodology as what we do with mixture of Gaussians, right? You're modeling the joint probability of your data, of your X. But if you just directly model the probability, this joint probability is kind of very difficult because this one has support size, this distribution, right? So like how many possible sentences you can have here. You can have support size is something like v to the t, because each word can have v choices and you have t words. So this is really an exponentially large family of possible sentences, and if you model this distribution, it's kind of challenging. So what people do is that people use chain rule. So you say this joint probability can be written as P of x1 times P of x2 given x1 times P of x3 times x1, x2 up to P of xt given x1 up to xt minus 1. And then you model each of these p xt little t given x1 up to xt minus 1. You model this conditional probability, using some parametric form, and then you learn the parameters. And the good thing about this conditional probability is that now you only care about the probability of one word, right? The probability of that one word is of size v, right? So like the support of this probability, right? So like the number of choices of words here is v. So instead of v to the power t. Okay, so the next question is how do you model this? Right? How do you build a parametric form for this conditional probability? So I'm not going to tell you exactly how you do it, but generally you just do it with a network. I'm going to tell you, there's some kind of details I'm omitting here, but roughly speaking, what you do is the following. So, the first thing you do, you have to do an embedding for the words. Meaning for every word x, you embed this, maybe for every word I, this is a word I, you embed this word into a vector EI. And this vector EI, let's say, is in dimension D. So every word will correspond to a vector. So you're going to have V vectors. Each vector corresponds to a word. And these vectors will be learned. So these are parameters of your system. So these are the parameters. And then after I have these parameters, what I'm going to do is I'm going to, after I have these embeddings, I'm going to put these embeddings into a gigantic neural network and let the neural network to output the conditional probability in some sense. So basically, roughly speaking, here you're going to have some model, which I kind of view as a black box. These days, people call this, use something called transformer. I'm not going to tell you exactly what transformer does because it's actually pretty complicated and it's kind of out of the scope of this course. If you can take a look at a paper or take some other advanced courses, but for the first order kind of concept, this is a black box, right? Actually, many people don't have to many people who use the transformer don't have to open up the black box. So that's why I'm only telling you what's the input and output of this black box. But this is a neural network. This is a kind of like complex neural network. And the way to use this black box is the following. So you just say, I have some sequence of words, right? x1 up to xt. I'm going to first encode them by the word embedding. I'm going to have e of x1 up to e of xt. So e sub xt. So these are vectors. And this transformer takes in the sequence of vectors. And then output you a sequence of vectors. So So the output, let's call them C1. I think let's call it, I call it C2, C3, up to CT plus 1. So, let's also just give a name for this transformer. Let's call this function phi theta. So this function phi theta, after given all of the input embeddings, it outputs a sequence of vectors. Each of these vectors, let's say, is still of dimension d. Even though this dimension d, in reality, this d might be the different d from this, but they are vectors. Okay, so after you get these vectors, then you can use these vectors to compute the conditional probability. That you use these vectors to predict conditional probability. So basically, you say that I have this. I'll use this, I guess, just. So now, after you get these vectors, C1 up to CT, so I'm going to use CT to predict P of xt given x1 up to xt minus 1. Okay? So what I do here is the following. So what I want to predict is this thing, right? So this is actually, this probability distribution is sometimes is a vector, right? It's a vector of dimension v. Because to describe this probability distribution, you have to describe P of xt is equal to 1, the first word, given x up to xt minus 1, up to P of xt is equal to v, given x1 up to xt minus 1. Right? So to model this probability, you have to model, kind of predict v numbers. And these v numbers is supposed to be sum up to 1. And how do you do this? This is kind of like, multi-class classification. So what you do is you basically say, I'm going to have a softmax of some wt times the vector ct. So let me specify here. So ct is a vector of dimension d. And wt is an additional parameter. This is a parameter that you will learn. So this wt is of dimension v by d. So basically, wt times ct will be dimension v. So you have like multiple. So for every possible choice, you get a vector, right? And then you apply a softmax to make them probability. So this whole thing will be in dimension v. So in some sense, this wt times ct is just the logits. And then you apply a softmax to turn them into probability, and that's your prediction for this problem. So in some sense, you just view each word as a class, right? You have v classes, and how do you predict something with? How do you do a classification with v classes? What you do is you first use a linear. This is a linear hat on top of the ct, and then you do a softmax to turn them into probability. So I think the definition of softmax, I think we probably defined this in one of the early lectures, right? So let me just define it again. So I should use this probably. So softmax is just like if you have softmax of a vector u is really something like this. Exponential u1 over sum of exponential ui, and then exponential u, say v over sum of exponential ui, something like this, right? So you turn the logits u into a probability vector, which sum up to 1. Any questions?
For the transformer, why would the input is 1, then the output is C2? Then C2 is the next word we're predicting.
Right. So I'm going to use C2 to predict X2. I'm going to use C3. You can index them in any ways. I choose this just to indicate that C2 is used to predict X2 given X1. So And actually, there's one thing I didn't tell you, which is actually important. So when you predict this probability, right? This is my model to predict the probability, right? I need to insist that I haven't seen other words. Like I have to insist that I only have seen x1 up to xt minus 1. Right? If I have seen xt already, I can just output the true value of xt I've seen, right? So actually this transformer, there are multiple versions of transformer. The transformer here I'm talking about, the term is called autoregressive transformer. This is just a name. What I mean is that you design this transformer in a way so that Ct only depends on x1 up to xt minus 1. So you design this architecture such that you have this property, such that the Ct only depends on x1 up to xt minus 1. So that when you predict xt, you are not going to be able to see any other words after xt. So that's why you have a proper definition of the probabilistic model. But this is like just to think of this as given. Like when you design, the transformer's internal property ensures you to have this, right? How do you connect all of the neurons, right? Ensures this property. The dimension of the embedding. So this in many of the dimensions, I call it D right now, but the dimension is just a parameter you can change. You can change it to anything. Of course, it has to be somewhat large, something like maybe 1,000, something like that. And the embeddings are learned.
Yeah, I'm trying to understand how does this relate to like what we learned about the one hot vector. Do we have to create that many?
That's a good question, right? So if you use one hot vector, probably you should use an embedding of dimension v, right? Because you have v choices. But now I think the embedding dimension is often smaller than the vocabulary size. I think the vocabulary people typically use is something about 40K, maybe 60K, something like that. Something on that level. But the dimension is probably 1,000 only.
Is the bulk of the dimensions like a hash function?
No, can you say it again?
Is the map of the bulk of the dimension something like a hash function?
You mean the mapping from the I to the EI? It's learned. So basically you just learn this. So you have E1 up to EV, right? Each word has a vector, and you concatenate them all of them as a matrix, and you view this as a parameter of your. This is a part of the parameters of your training. Okay, so now the final step is just that after you already define a prediction, you have to define a loss function to learn the parameters. Right? The parameters are, the question was great, like the parameters include E1 up to EV, also include WT, right? And that's it, right? That's all. Also the parameters in the transformer, which I didn't specify. That's a neural network, which is viewed as a black box. So, and now you take a loss function, right, which contains all the W's, which is a function of W's, the theta and the EI's, the E, and then what this loss function is just the cross entropy loss of all the positions. So cross entropy loss of all position I. And if you really think about what's the cross entropy loss for the softmax for this kind of things, it's really just this. But you don't necessarily have to really exactly see why it's this. But it's really just the minus log probability of PT at xt. So if you call this thing PT, suppose we call this PT, then basically the xt's entry is minus log p xt entry is this is the xt's entry of that vector pt, and this is just the cross entry loss. But don't worry if you don't get this line. It's really just empirically, you just have to, when you implement this, you just have to call the cross entropy loss and give it to it. I'm running a little bit late. Any questions? Okay, so actually there's another small thing I didn't, I cheated a little bit. So here I'm taking, so this definition, I can only define it for t is 2 in some sense. I don't have a prediction model for x1. I only have the prediction for x2 given x1, x3 given x1, x2. I didn't have a probabilistic model for x1. Empirically, people just forget about it. Just don't use it. It doesn't matter that much. You can try to fix it to make it principled, but I don't think it matters that much anyway. So just because you have so many probabilities to model, and if you ignore one of them, it's not a big deal. Okay, so now let me talk about how to adapt this language model to downstream tasks. So I've erased the fine-tuning and the linear probe, but if you can still do those are very general. You can use those fine-tuning and linear probe for almost anything. So, and for this kind of like language model, the way you do fine-tuning and probe is just that you it's just the only thing you have to decide is that which output you should use as the representation of this document, right? So you have so many outputs here, and which one you take as the representation of this sentence. So you just take one option is you take CT as the representation, and then you add some hat W, and you get W transpose. This is your prediction model for downstream tasks. And then you can choose to only fine-tune W, or you can choose to fine-tune W and the parameters that you use to compute CT. Right? The parameters used to compute CT are those parameters in the transformers, those EIs, those embeddings. So that's easy and just because it's generic. And for language models, the interesting thing is that you can also do this with some other ways, where you can do adaptation with other ways. So one way to do this is so-called the zero-shot learning. And here it's just very easy. So basically, whatever task you have, you just turn it into some questions or some kind of like closed test. Like you have a blank to fill in. And then you just give it to the model, and then the model to generate the next word. So basically what I'm saying is that you just say, for example, suppose you just turn you can have a x, which is just this model can take in a sequence of words, right? You just say maybe is the speed of light. Suppose you care about the speed of light is constant or not, and you just turn it into a question, right? You call this this is x1, x2, x3, up to xt. And then, because this model can generate, maybe let's say this is xt minus 1. And then you use this model to generate xt. Because this model can do conditional generation, right? You can, given x1 up to xt minus 1, you can generate xt. And given x1 up to xt, you can generate xt plus 1. You can just keep generating the tokens afterwards. And you just put this into the model and let it generate. And if you generate the next word is no or yes, then you get the answer. And maybe sometimes it generates something slightly different from just yes or no, then you have to pass the answer in some way. But you just let the model to generate the answer. That's one way. And so basically you are using the generation power of this model. That's probably the important thing, right? Because given this model, so basically here the important thing is that the way you have this model makes it that given some sequence of words, you can generate the next token. And then you can feed back this new token to the system to generate another one. And you can keep generate. So that's why this gives us opportunities to have other adaptation method which based on generation. And another kind of like a even more intriguing way to adapt is the following. It's called in-context learning. So the in-context learning. So here you are dealing with, the so-called few-shot cases. So you have a few examples. So suppose you, and let me just give an example there are so many flexibilities. I'll just show one example. So what you do is you just concatenate all your examples into a so-called prompt. Concatenate examples into, in some sense, actually in the language of this lecture, we call it document, right? But if you look at the paper, it's called prompt. So what I mean, it just means you concatenate all of this into a sequence. For example, suppose you care about learning how to add up two numbers. Suppose you have a question Q, which is something like 2, 3 is what? And then you have some examples, right? You say you know that this is 5, so this is your X task 1, and this is your Y task 1. So you just concatenate them into a sequence of tokens, so like this, and then you just keep concatenating, and you say Q6 plus 7, no plus. I choose to not use plus because I want to make it difficult, right? So something like this. You are trying to learn what this symbol means, right? So and then this is X task 2 and Y, and then you concatenate Y task 2 here. So you say answer is 13. And now suppose you just have two examples and you want to learn, and then now your question is 15, this symbol 2 is equals to what? So you concatenate all of this together and you call this x1 up to xt. And you give this x1 up to xt, the sequence of all the symbols to the model, and let it generate, and then you ask this sequence to generate xt plus 1. So use this to generate xt plus 1, right? Or maybe even xt plus 2, so on and so forth. And it turns out that if you give these things to the model, and they will generate something reasonable for you. So it will generate something. For example, for this case, it will generate A 17. And then you got the answer. The answer is 17. So, and you see that this in some sense says that you learn the downstream tasks. You learn that this symbol means addition from this. I'm not sure whether this is a little bit abstract, but I think what I can do is the following. So I think this is about time, and we can stop. We can stop the class, but I can show you some examples, just live.